coming up. Okay, great. So let me just run it. So we can first look at the data. Okay. What's this one? I guess you guys get what I see here, right? Yes. Okay. So I do want you to pay attention to several things here, before we really go to the details. First thing is, you see this huge background, right? And keep in mind, all this background, so-called background, comes from the sample. It's not from the category, it's not from the container, it's not from the air, okay? It's from the sample, because when measuring the interface samples, we should always measure the background, actually carefully, which means we measure the empty category with the same size, the same exposure time, right? So we should measure that very carefully, and we deduct that portion from the total the measurement. I mean, including both the container, the air scattering, the samples, and from that data. And then you get something like this. Okay, so there's no contribution from the air, from the category. And what this is telling us is there are indeed a lot of amorphous components in the sample, right? So you see this big bumps. If you move the cursor to this peak, you see the d-spacing is about 7.4. Do you guys recognize the number? Right? You see the d-spacing. You see the d-spacing in the top. I mean, in the bottom, right? So you see the d-spacing there. 7.4 angstrom is a very large d-spacing. No, because, for example, if we talk about the layer materials A and C, the d-spacing should be around like about less than 5 angstrom, something. So 7 angstrom is pretty big, and it's not coming from a crystallized structure. And we can also tell from the broad peak, right? You see the peak, how broad it is. It's hugely broad. And same is true also for this one. So you see there's two peaks which are so broad, and they're coming from the amorphous components. So when we look at this data, even before we go to the PDF, we should recognize, okay, there's abundant amorphous components in the sample. And that has a significance on our data analysis. We do not want to deal with this amorphous part, because it's very difficult to find a polynomial to fit these two things, right? And second of all, our focus of analysis of the diffraction data is on the crystals. So we mainly focus on the crystalline parts. So we do not have to include the broad amorphous peaks. That is making the job much more challenging and quite not worth it. So we need to wisely choose a range for data analysis. So you see here, we actually started from somewhere around 3.5. That's our starting point. Why we chose that? Because we, after some preliminary analysis, we will recognize this is actually coming from the lithium hydroxide. Okay, this peak contains information, so we need that one. We keep it, and anything below that, it's not contributing much to the information, the crystalline information. So just this, exclude it, right? So we're throwing away this part, from the data analysis. And for the high angle, you see the peaks are getting weaker and weaker as we go, higher and higher in the 2 theta. That's also happening here. So actually, it shows a point that meaning that we still can see the clear peak. But here we can see already the peak is kind of weak, right? So the higher end is usually, you can choose it on the basis of finding a well-defined peak. So for example, you probably can also limit your higher range to somewhere around 11.3 or something. So you do have a clear peaks. Otherwise, it becomes more noisy. Right? So this is the selection of the data range, and that is shown in the info file. So we define the value for star X and the value for the finish X. This is basically the data range that we would fit. It should not be the total range by default. It should be selected. Okay. The selection is based on your observation. So you need to observe what your data looks like, and then make an educated choice. What's your range for fitting? Okay. So broad peaks and low angle indicating amorphous faces. Number 1 observation, and number 2 observation. I think you need to pay attention to the numbers. So like I mentioned previously, we're mirror interface, which are indeed very weak scatters. So you see the numbers. The numbers, if we're talking about the peak intensity, if that one subtract the background, so you see the strongest peak has in peak intensity about 30, I guess. It's somewhere between 30 and 35, even less than 30, actually. So this is the strongest peak we have. And we must recognize this is a very unique thing. You're using a very advanced synchrotron. You're exposing your sample on the order of from like 10 minutes to even 20 minutes without any filter. It's full flux. It's enormously long-time exposure. And eventually, the count you get for the strongest peak is only around 30. So that is saying something. That is telling us the challenge of mirroring the interface samples. It should not be regarded as some kind of routine job, right? If you're mirroring AMC, for anybody who has went to XPD, understand that you should lift out some of the filters, otherwise you will get saturation, right? You should limit your exposure. You can get a high quality data within like 20 seconds, at most 1 minute. And the counts you get for strongest peak is usually on the order of hundreds or thousands, right? But here we're talking about the strongest peak that only has about 30 counts. So we can have appreciation. This is indeed a very challenging environment. But I think we have seen very nice progress in sample preparation. I believe more and more people in our group are capable of preparing interface samples for the environment. That's very important. That's step 1, right? So you need to collect the samples that is kind of sort of dense and well sealed, well protected. And the second step is making measurements, and you should lift out all the filters, let them fully be exposed to the beam, high flux beam, and you should expose purely at least 5 minutes or 10 minutes something. And also the background should be carefully taken. Okay, the background is a must for the interface measurements, even for the XRD. We must measure the background very carefully. So that's something you need to pay attention in terms of tracking the data. And the second step is also challenging, and that's why we're having this kind of lecture, which is analyzing the data. So how to analyze such a pattern? One thing is you see the peaks are weak. They have comparable intensity with the background. That's very tricky. The second thing is you do see the peaks, they have very diverse properties. Some of them are pretty sharp, right? So we have this kind of sharp peaks, very sharp peaks. We also have those kind of broad guys. You see this is very broad peaks, somewhere here, somewhere here, somewhere here. They're all broad peaks. It's a mixture of both sharp and broad peaks, which means one thing is they must belong to different phases, right? The second thing is these different phases, they have a very unique, they have very different microstructures. And what that means more specifically for the refinement is your parameters for the profile function are very different. Because when we talk about the peak shapes, the widths, we're basically talking about the profile function. So the parameters for profile functions, they're very different. And to give you some kind of an idea how challenging it is, let me show you, this is a folder. This is one of the folders I created when I was working on some of the data. And so I was working actually on two data. But this folder contains 57 items. And you see, contains about around 20 input files. Why is that? Because you need to be careful about each step. It's not like refining MC, you just throw in the last parameters and just let it go. And 99% of the time you get a refinement. But for this kind of data, you really need to be careful, So each time when you make a progress, you always need to save the file immediately to make sure, you're not you're making random trials, but you're getting closer and closer to the good refinement, which is a step-by-step way. It's unlikely that you'll do a good refinement just in one step. So you already need to figure out a way by yourself how to get a good refinement specifically for your own data. Okay, so that's something that is not very general, but I can give you some guidelines. And that's what I'm going to talk about today. So the guidelines is, first, there are indeed sequences. Okay, I want you to keep in mind, sequences matter a lot for refining the interface samples. The interface samples, they have a very weak intensity, so we always need to have an educated sequence of refining the parameters. Okay? So, a small test here. What kind of things do you think we need, or you can remember that we need to refine, refinement? What things need to be fitted?
That is parameter.
Yes, that's parameter.
B value.
B value, yeah.
Atomic position.
Atomic position, yeah.
String.
String. You mean string? Yes, string is part of the profile function.
Oh,
right?
yeah.
So, yeah, so it's actually that relates to the profile function. Right? Yeah. How do we deal with the background? Do you remember how we deal with the background? Yes, polynomials. Right? So basically, background is a polynomial. So that's very easy, right? Anybody who went to college, you're familiar with the Taylor series, Taylor series is always a good approximation of any function. Taylor series in essence is just polynomials, right? So we need the background. We need to fit that one, and that is very important for interface samples for the reason I just explained. We have huge backgrounds, and from my experience, the tricky part is you need to figure out how many polynomials you want to vary per background. So because background function basically, so this is this time. Because background function in essence is a polynomial. So let's say if you just put in one number, it will be a straight line, right? If you put in two numbers, it will be a line with a slope and the intersection. If you put in three numbers, then that will be quadratic, right? So you'll be having a quadratic function, and then you have a cubic, etc., etc. So you see that the more numbers or the more variables you put in the background, the more flexibility it will have. Right? It can give you some very exotic shapes, but we always need to keep in mind because if the background is too flexible, the change in the background will eat the intensity of the peaks. You know what I mean? Get my point, right? Mm-hmm. Yeah, because a small variation in the background would actually eat the intensity that is supposed to attribute to the peaks. That's the challenging part. And this is different from AMC, because in AMC, your background looks like just almost a line, a straight line, right? And also because the background is so small compared with the peak, no matter how it varies, it's not really doing anything to a peak. Your peak is still mostly your peak, but your background, is just doing a very limited, influence on the peak. But here, on interface sample is different. So we need to, Sean has already mentioned several things. That's very good. And also we need to keep in mind, we need to deal with the background. That's the tricky part. We need to be wise about how many variables or how many parameters we need to refine for the background. It should not be too large. It should not be, let's say, okay, I feel this is a very complicated background. Why don't we just throw in like 10 numbers? So you have a 10th polynomial, 10th order polynomial. Then you'll definitely get a mess with the data. But you cannot put it in a too simple way. Let's say, okay, I just put in 2. Obviously, it doesn't work, right? You can never approximate a function with just a line or even a quadratic line. It doesn't work. So my experience is you may want to start with something like 4 or 5. 4 or 5 parameters, so which is about like a 5th order polynomial for background. So they have enough flexibility, but not too much that would influence the peaks. And then you can see whether your background is doing too much variation, too much complicated, then you can reduce the number, let's decrease from 5 to 4 and do refinement again, right? And see whether that improves. So it's a very time-consuming process. You have to be prepared for that. But we just spend a little time discussing the background, but that's not saying we need to refine background first, okay? And Charles mentioned last parameter. So usually, that parameter is the first one to refine, but you need to pay attention to but. For the interface samples, you see, this is already a refined pattern. You see, we have this metal, right? It's always there, the tungsten that you scratch from the anode. We have the lithium hydride, and lithium chloride, and lithium hydroxide. So usually this metal is a kind of a very dominating phase in a sample. And that means we are already very certain we have this metal. And so the trick is, for the experience is, you do not want to refine your this metal peak, that's parameter in the beginning. You just put in like a standard one, or the one that from our previous refinement, right? So we have several works published on interface calculation. So you can check the last parameter we got in our previous refinement and use that for the lithium metal peak. This is kind of a sort of a refinement strategy, because if you fix the lithium metal peak in the very beginning, and the program may very likely lose the focus, because because there are several variable things at the same time. You may have a hard time trying to identify the position of this metal peak. So we can just first tell the software, I directly tell you, this is this metal and this is that parameter. And do not care anything about this metal. Focus your attention on other things. That will make your refinement much more stable. Okay, so this is one of the strategy or tricks that you need to keep in mind. Fix your lithium metal capacity at the beginning. And the same may also be true for lithium hydride. So you see the lithium hydride, this one, right? So lithium hydride also has very sharp peaks. And that's the basis of one of our previous discussions. We identified the presence of lithium hydride, and we analyzed the properties of lithium hydride, especially how it is in huge contrast to the lithium fluoride, which has very broad peaks. So these two components, they have very different properties in interface.
So in general, if a phase is more crystalline, so it's best not to be messing around with the lattice parameter for that phase.
Very good point. Yeah, exactly. So if that one has very sharp peaks, the general strategy is you identify the lattice parameter. That's very easy to do. For example, this is the lithium hydride. So you put a cursor here, you see this is the 111 peak, right? And from the D spacing of 111, the D spacing can be directly read. So from the D spacing of 111, you can deduce, even using your hand, what is that? That's parameter, right? And that is a very, very good approximation. So you just put that number from estimation in the input file and do not fit it in the beginning. Okay, so yeah, that's a good point. If you have a very sharp peaks, that's usually the way to do it. Okay, and so we talked about the limiting, actually adjusting the variables for background, and also fixing that as parameter for sharp peaks, and also we can look at some of these broad peaks. This one's lithium fluoride has hugely broad peaks, right? So this is resonating with the point that lithium fluoride is highly narrow crystalline in the interface. It has some very unique properties. The other phase is lithium hydroxide. So we can tell this peak is lithium hydroxide by what we did last time by going to J. So you can use J first to help you to identify what are the possible phases. So J will probably tell you, this is very likely lithium hydroxide. So you can make a mark, find the reliable lithium hydroxide crystal structure by using the database I recommended last time, right? So make sure your crystal structure is trustworthy and put that in your input file, and then during the refinement. After refinement, you see this one has a very broad peaks. The other thing is, in fact, if you look at the peak, the width of the peaks, this is also peak, in fact. You see, this is also peak, hugely broad. This is also hugely broad. The peak width of lithium hydroxide, in fact, is highly anisotropic. Right? It's a difficult phase to deal with. It's highly anisotropic. So when you have this kind of a situation, you can first, just treat it as a normal phase, and the software will give you this kind of very hugely broad peaks, right? At a later stage, if you realize it has this very obvious anisotropic broadening, we can consider integrating a more advanced profile function. We haven't talked about profile function yet because it's more like sort of a routine choice. you see the profile function we use for all places is what we discussed the last time. This is basically the volume weighted peak width with both the crystal size and string contribution. And so these two functions define the profile function we use, right? And also, I think last time somebody raised a question about the choice of numbers. And for the first one, the 1 and 0.89, those are kind of a by default value, and we normally do not change, right? And also, I hope you still remember how to define a fitting parameter in the parentheses. So if it's just if it's outside parentheses, for example, about a scale, right? There's no parentheses, so we're just going to use add symbol. We'll put an add symbol and then put a default value. Okay, but if it's in the parentheses, then we need to first put an add, followed by a comma, and then the guess value. Okay, so they have a slightly different grammar, and make sure you always, make no mistakes about grammar. So we use the same profile function for all these spaces. You see the lithium metal and the lithium fluoride, the lithium hydroxide, right? So you see the lithium hydroxide, as I mentioned, it has anisotropy broadening. I commented out this line, which is called the Stephens tetragonal height. And this is the advanced profile function that is used to fit anisotropic peaks. And as a Stony Brook student, you should be proud of this profile function because it's written by Stony Brook professor Peter Stephens from physics department. He's very dedicated to the direct community. So the whole profile function for all the space groups was written by Peter Stephens, and his function turned out to be very useful, very flexible, and is very well received in the diffracting community. And that's why his function actually goes into the TOPAS software. If you meet other symmetries, so this hydroxide is a tetragonal. If you meet other symmetries, so what you need to do is, you just search your Peter Stephens function in Google. So I directly search this keyword, right? You search this in keyword, it will bring you to the more details about other symmetry systems. So you see here, it has basically the keywords for all the symmetry systems. And for the same symmetry, for example, for tetragonal, it has the low and the high, depending on the highest point group you have. If you have a very high symmetry point group, then you will choose the high profile. And also, this one tells you the number of parameters you should put in the function. For example, for the tetragonal, there are 1, 2, 3, 4, 5 parameters to fit in this profile function. So you need to put in 5 parameters, and the way to do that is, at, comma, a number. By default, you can just put in 0, right? And then comma, and then at, comma, another number, and then you write that for all the 5 parameters. And that's the way to do the Peter Stephens fit for the anisotropic case. Okay. So at least I think you should have knowledge about this the anisotropic problem profile function. The other thing I want to pay attention to is the scale. As I mentioned, the scale is easy to fit, right? It just simply defines scale and followed by add and a default number. But as I mentioned, because the intensity is extremely weak, you always want to put in a very small number for this one. Okay, so this number for AMC can be like somewhere 10 to the order of -5 or -6. But here, it's very common they are 10 to the order of -7 or 8. So the strategy is you always start your scale scale parameter, the default value was a very small value. You already tend to the -8 or 10 to the -9. When you start with a very small scale value, that will give you a more robust refinement. If you put a big value to start with, it's very likely your refinement will crash after just the initial runs. Okay, so always start with a very small value for the scale. Okay. And we can have a more check. We can look at more details of the refinement in profile. So I think we have went through those things. Those are just exactly the same as what we see in the AMC refinement, right? So input file, we define, we fit the background, we define the range we want to fit, and we put in the Lorentzian polarization parameter, and we fit the zero error, and also you have with some sort of distance parameters, and also you have this simple axle model to account for the asymmetry of your low angle peaks, and we're creating a wavelength here. So those things are the same. And last time we talked about the multiple phases. And it's also the same for the interface, which contains multiple phases. You start your phase with the str keyword, so that the program know you are introducing a new phase. You define your profile function using these two, and your scale, and your phase name, space group, last parameter. And because this one is very simple, this method is BCC, it has only one site, your unit in the unit cell. And that site is fixed, right? There's no atomic position to fit. The only thing to fit about intensity is the BQ value. Okay. So for BQ value, I want to mention that because sometimes when you have this kind of challenge data, some of the numbers may go very exotic. So let's say you have a BQ of -2, which doesn't make sense, right? Because the BQ value is supposed to be a positive number. So the way to define the range of your fitted parameter, let's say we ask the software to do the refinement such that the fitted BQ number should make sense. It should not be negative, right? It should not be too small. It should not be too large. For example, we can define the minimum of BQ. Let's say maybe 0.1. 0.1 is already very small. And keep in mind, usually only heavy atoms have small BQ, right? We talked about this before. For example, transition metals in the AMC, they may have a BQ about a fraction, like 0.2, 0.3, something. That's for transition metal. Okay. And if we have light elements, they tend to have a bigger BQ value. So for example, for oxygen, in your crystal, the oxygen may have a BQ value around maybe 1.5 or 2. They all make sense. But it doesn't really make sense if the oxygen has BQ value of 10, right? Well, that means your oxygen is basically very blurry. The oxygen is contributing negligible, very small intensity. So let's define the reasonable range, like minimum to be 0.1, max to be 0.5. Okay, so and this also applies to every parameter they want to fit, right? And if you pay attention to the grammar, we must have a semicolon here. This is required, the definition of a minimum and maximum. And also same true, let's say if you want to fit the last parameter, but you believe that last parameter should be between 3.5 and 3.6, then you do the same thing, right? And you do the same thing, and you just also say the minimum is 3.5 and maximum is 3.6. Okay, that's way to limit the fit data range. So that's for the lithium metal, and for lithium hydride, it's the same thing. Okay, so you see, I didn't really fit those parameters. And is it FM3M? Every position is fixed, so we do not have any atomic position to fit. And we have the BEQ values, which seems to be reasonable in general. And we have lithium fluoride. Okay, so the same thing. But there's one thing I want to pay attention, to is look at this number. This is only around 4 something, right? If you check this number for lithium hydride, which is 42, and lithium metal, which is over 3,000. So you see, this number relates to the microstructure, correlate to the crystalline size you have. If you have a very small number for this one, you're supposed to get pretty broad peaks, suggesting your structure should be very narrow. You can check the meaning of those parameters in the description of this profile function. So you see that the first one K is wrong. So this is a dV, right? And dV is basically related to the size of the crystals. So if you have a very small number for dV, then that means your crystalline size is very small. Okay. And for lithium hydroxide, we also do the same thing. You also see a very small number, 0.4 for the dV value. That's suggesting the nanocrystallinity of this phase. And for lithium hydroxide, we can refine the last parameters. And it does have freedom in atomic position. So we see both the oxygen and the what's this? Actually, this is oxygen. Oh, this is hydrogen. Okay. So this is hydrogen. But hydrogen is so weak in scattering, right? So basically, this one is more symbolic. So, so you see they're both the oxygen and the hydrogen positions, they can vary. So those two can be fitted. And similarly, you can define your reasonable BQ range by using minimum and max sentences. Okay. So yeah, so that's pretty much how we do the refinement involving the different phases. We talked about the choice of sequences, right? So the sequences, well, first you should gather a template either from me or from other people who has done refinement on the interface samples. That will save you a lot of time. By lot, I mean days. So you should have a good template to start with. Once you have a good template to start with, then it's possible that you do not have to do too many things in the background. You just leave the background there, right? And your background, the order of polynomials or number of variables, that should be reasonable. And what you need to do is do not fit your very sharp peaks which are basically this metal and this hydride, and your nano-sized phases like lithium fluoride, lithium hydride, and also lithium oxide. Sometimes we have the lithium oxide. Okay, and it's very likely the lithium hydroxide phase in your sample is anisotropic. So when you see it necessary, you can introduce the Peter-Stevens profile function into the lithium hydroxide structure into the refinement. You can first, make all the parameters zero in the Peter-Stevens the profile function. So it requires 5 parameters. You can put them all zero and just let the time around and see how it goes. Okay. Yeah, you can define the reasonable range for your B parameters. It should not be very small, should not be very high. You can define them using the minimum and the max their definition. Okay. So yeah, other than that, I guess that's pretty much what I want to share with you today. Yeah, we may still have some time for questions. Do you have any questions?
The dv value for the area function, when you define it, you get a number. Does that directly correspond? I mean, can you get some idea about the crystallite size from that number?
It's related, but it's not a strict definition. So for example, if you have a dV value like 4, right, for one phase, and another phase is 400, you definitely can tell that one has much sharp peaks, that's for sure. But if you say you have 4 for this phase, and you have 5 for another phase, you cannot really tell, whether this one has a smaller crystal size than that one. The reason is, it's still correlated with other contributions, for example, strain. They still have a correlation. Okay. It's already reasonably separate, but still they have correlations. So it's not really a very accurate number to describe your crystalline size. Okay. Do you have any other questions?
So for can you hear me?
Yeah.
Yeah. So besides, since for the interface sample, the background is usually very strong compared to the sample signal. I think before you mentioned that we can use the dummy phase to solve the background signal. Is this? Can you elaborate a little bit more on the concept of dummy phase?
Oh, the dummy phase. Oh, okay. Did we have a dummy phase in this info file? We didn't, right?
No, just you mentioned this before. I'm kind of curious.
Oh, right. Yeah. In your case, in your case, I think we mentioned the dummy phase. Yeah, but it was not included in this info file. So yeah, dummy phase is okay. This is beyond what I was planning to share today. Dummy phase is basically the bell refinement. So we have 2 kinds of refinement, right? One is called a real refinement, and the other is called the bell, or there's another word called there's another name very similar to the bell. What's that? There's another word that is also the same meaning as the bell. Pauli, yeah.
Yes.
Pauli and the Lebel refinement. Okay, they are basically they are having the same philosophy. So you need to know that there are two kinds of refinement. Rural refinement is what we're doing here. It's called structural refinement, which means we count the intensities using the structure. Why there's a peak? Because we have this intensity. We have this transition metal in this position, and it's giving rise to the intensity, right? So the intensity you see, the diffraction, is related to your structure. What kind of atom do you have? Where they are? They are related. So it's called structural refinement. Okay, rare refinement. And Pauli or Lebel, that's also called a structureless, LESS refinement. Because in those cases, your intensity is not related to your structure. It doesn't really care what kind of atoms you have in the structure. What it really cares is where are the peaks or the position of the peaks, right? So what defines your position? Lattice parameter. We only need your lattice parameters because once you have lattice parameters, including both the ABC and the alpha, beta, gamma, then you and of course coupled with space group, right? You know the position of the peaks. And your intensity is approximated by a pure mathematical function. It is not correlated with a function structure at all. Did I make myself clear?
Yes. So it takes care only of peak shape and use that information to kind of trace back to what the structure is. Am I correct?
Can you say it again?
So it don't care about the structure. It only fit peak shaped and then use that information to.
Yeah, you can sort of say it that way. And in fact, the ironic or interesting is in the very beginning, people imagined this to solve the structure. Why is that? Because people need to get accurate intensity information from each piece. Okay, so for example, I can index this phase, so I know HKL, but I need to the accurate intensity from each phase, from each peak. Then how I do that? I do that by doing the structureless refinement first. I just approximate the intensity of peaks using mathematical function, and not the sum structures. And after I get the intensity, accurate intensity for each peaks, then I start analyzing, and then I try to deduce what the structure should be like. Hope I'm not getting confused, but the take-home message is Lebel refinement is structureless. It only takes in lattice parameters, and also of course the space groups. It doesn't really require your structure information, what kind of atoms you have, where they are. It's not needed. Okay. So dummy phase is basically a Lebel or the power refinement. And why we use that? We use that because sometimes the background is so complicated, we just throw in a Lebel component. So we do basically a refinement that is a mixture of both railroad and Lebel or pi. Okay, so for the rail refinement, we get information that of our interest to us. So we get information about lithium metal, lithium hydride, lithium fluoride, lithium hydroxide, and those kind of phases. And for the dummy phase, its contribution is actually to give us a better fitted background. Okay. I don't think that we want to dive into the dummy background today, but yeah, that's a good point that you brought it up. So what I can suggest at this time is, next time when you deal with your own interface sample, you first can try the template I gave you today. If you still need problems, let's sit down together and see whether we can improve by introducing dummy phases. It's not very necessary for every data. It really depends on how we analyze the data. But it's good that you brought this up.
Thank you.
Yeah. Okay. No more questions? We're good? Okay. Then we can conclude today.